Thank you very much. This is very difficult for me because I need my hands to talk, and now one of them is occupied. So I'm going to at least leave one free. So this is me, and it says Plus Optical Networks Group, because this year is actually 30 years of the Optical Networks Group. And all this work I'm talking about is done by many generations, about 8 generations of students who've gone through the group, and countless research fellows. In 1994, this was the first academic systems engineering research group in optical communications, and it was supported by my 10-year Royal Society URF, which is an amazing scheme. If you have any opportunity with Tom, you'll benefit from every second that you have under it. It's now 35 people strong and internationally leading, with a unique combination of expertise on networks, transmission, and devices, with a world-leading experimental laboratory. I'm taking the liberty of talking about the group because I think 30 years to last in UCL with a group that people said couldn't exist really outside of industry. Is a bit of an achievement, so please forgive me for bragging. And now it is really, now with the industry defunct, it is the only optical communications systems and networks group in the UK. And with numerous records, we've shown transmission of over 200 terabits per second. Just for comparison, that's 100 million simultaneous Zoom calls, just to translate it. And the experimental work is supported by powerful analytical and numerical modeling tools, which are very essential to go along hand in hand. We've had numerous collaborations with industry, and the experimental testbed that we have, this multi-wavelength transmission and network testbed, it's used to support research in industry and academia worldwide. And many concepts have been taken up by industry, with one of the greatest pride of the group is the careers supported. Major prizes for PhD students, 13 IEEE Photonic Society Postgraduate Awards. We're leading the world in that. Numerous prestigious fellowships and awards, numerous PhD graduates and research fellows, and most are now industrial leaders themselves, industrial and academic leaders themselves. So that's tremendous source of pride, some of them in that photo at a recent ECOC conference. So I'm going to talk a little bit about the cloud, and I wanted to talk, being in UCL, we have to talk about the start of the cloud. So the cloud, as we know, it started from Porthcurno, in the UK at least. The first cable, first transatlantic cable out of the UK went to India, or it was between India and Porthcurno, which is a small little beach in Cornwall. It is also a site of PK Porthcurno, the Museum of Global Communications, where I'm proud to be a trustee. And this led to the Porthcurno Telegraph Station. And within 2 years, there was the beginning of the cloud. Look, there were numerous cables going from between UK, North America, India, and Australia. The person behind this was John Pender, who led the Eastern Cable Company, and he also gave some money to our department to set up the Pender Laboratory and the Pender Chair, the most famous electrical engineering chair in the world. Within just a few years, there were 600, an email to a telegram to Australia from London took only 10 minutes, and 600 messages were leaving UK via Cornwall every day. So that's kind of the beginnings of the cloud. And the other UCL connection was via wireless through Marconi, and hopefully all of you know the story, but those who don't, here it is. This is where Marconi did some of his fundamental work in this hut, also in Cornwall, just one little cove away from Porthcurno. And because he didn't have money he came to the UK from Italy because the UK had a navy, England had a navy, Royal Navy, and so he went to Fleming, the first professor of electrical engineering in this department, in UCL, Department of Electrical Technology, to build him, Fleming, whom we know by his left and right hand rules, to build him, and by the valve, to build him the equipment to the transmitter and receiver for his wireless transatlantic communications, which his customers requested to do. This is very similar of industry these days. They want to see proof of principle experiment. So they built this 20-tower antenna at Poldhu, and in 1901, first transmission took place and was confirmed in 1902. Over 3,000 kilometers. So these two elements, the wireless and the fixed, became part of the cloud. So what is the cloud today, and what's driving it? So the cloud is the interface between the real world, all the different applications, some of you that you've heard about, all the IoT traffic is in the cloud, is going via the cloud. All the application, 99% of all data is going via the cloud. And the cloud, it's sort of the infrastructure and the bunch of data centers are interface between us and the cloud via the optical networks. So 99% of all data is going over optical fibers. Most of us and you hear a lot about 5G, 6G, the need to develop. But in fact, there would be no 5G, 6G, or XG if there is no advanced optical fiber communications infrastructure, advanced intelligent infrastructure to support it. And there's much less heard about that. So it's extraordinary. The cloud, what's driving the cloud is immense growth of data. This is from Seagate. Data from Seagate, you can see from 1979 when they started selling their first memory devices to 2021. So, since then, imagine more growth. There is more growth in the last, in the couple of years to 21 than there were for the previous 36 years. That's extraordinary. So there is now several zettabytes of data, or there were in 2021, and projected 175 zettabytes of data as measured by storage by Seagate, so probably much more. So that's been fueled by migration of workloads to the cloud, and that's been the effect of the transformation, a digital transformation of business and society. And that cloud infrastructure is critical. It's been enabled by some 6 billion of fiber kilometers installed only since 2005. So that's, again, we don't hear about it. It's kind of assumed that optical fiber infrastructure is kind of a bit like plumbing, a bit like digital plumbing. But in fact, if it doesn't evolve, never mind being hacked, it is carrying 99, so if somebody is hacked, that's one person, that's carrying 99% of all digital data. So the security implication as well as capacity are also very important. So the physical optical network is defined by its physical and network properties, and it must be able to respond to the application requirements. Those are capacity and delay. You need to be able to provide whatever network capacity you need, when you need it, and where you need it. And it is very interesting that there are very few applications, think about it, that the optical networks go from networks on chip to in between chips within computers to a few kilometers, so that's from interfacing qubits that's nanometers, micrometers, optical data centers, kilometers, access, tens to hundreds of kilometers, core, thousands of kilometers, and multi-thousand kilometer submarine networks. We're operating over 12 orders of magnitude. Now, which other technology you can think of that operates over 12 orders of magnitude? I leave that to you as a challenge. And my title, Seeing Through the Cloud, we need to design an infrastructure that's optimized for performance and efficiency, which is kind of measured in different ways. So first, maximizing capacity. This is what an typical optical network looks like, or a typical optical system, a point-to-point system. It's number of transmitters carrying many different wavelengths of light, and on the other side, receivers, going through optical fiber, periodically boosted by optical amplifiers. Depending on the application, the transmission spans are between 50 to 100 kilometers. And every property of light is used to code information: phase, amplitude, polarization, and many frequencies of light. And the coherent receivers that much of the technology has been invented and developed at UCL with advanced DSP, is one aspect of where we can introduce network intelligence. So these systems form links and networks. They're all interlinked on different scales. And the problem with the optical fiber channel is that it's nonlinear. The material is material out of which fibers are made. Is glass. That glass is its refractive index is energy dependent. So more data, more nonlinearity, and the fiber diameter is small, 10 microns, so even a few milliwatts of power gives a massive power density. That's power per unit area. So that causes, particularly in intensity, in phase modulated systems, so systems that rely on phase and polarization, distortions, which result in errors. So there's a lot of work to fight these distortions, how to maximize the signal-to-noise ratio. So the capacity is given by bandwidth times the logarithm of the signal-to-noise ratio. So we can try and maximize the signal-to-noise ratio by, for example, modulating a signal in a particular way that is less impervious to distortion. But look, that SNI is within the log. So it changes, even if we maximize it, it changes very slowly. That log function will even 3 orders of magnitude in SNR gives you less than 10% increase within the log. We can increase the bandwidth that's accessible in the fiber. So that's one of the directions, and we can use different types of fibers that are not they're less nonlinear or not nonlinear at all because they use air in the core, or multiple cores within the fiber so that to increase the amount of data transmitted. So that's also part of all this research. We don't really care about what type of fiber. We can tell you how much you can transmit, point to point, or in a network, in any fiber, after some research. So I've talked about the nonlinearity, and just to amplify about the signal-to-noise ratio, we can increase. So this is a graph of generalized mutual information, which measures capacity against the signal-to-noise ratio. So we can go up in order of modulation, which means that these constellation points become closer together. That means we can transmit more information, but because they're closer together, we can transmit more information, they're closer together, they're more liable to distortion. So that's harder. So by designing particular constellations, for example, moving certain points away geometrically, or probabilistically giving higher probability of transmission to certain constellation points. This is, by the way, this is what your data looks like. It looks like this constellation. Can achieve some changes, some improvements. a lot of improvements, enabling the cloud. What's enabled the cloud is DSP and Moore's law. This is what was the first coherent Sienna chip. It operated at 40 gigabits per second with a power, using power of 1 watt per gigabit per second. This is the newest chips that are coming out from all the suppliers. This one is from Nokia, but there's also Infinera, Sienna, Acacia, using the 3 nanometer process. And that chip has to do a lot. It has to have it has to do clock and data recovery, forward error correction, equalization for polarization, for polarization mode dispersion, for phase noise, and nonlinearity compensation. So it's very, very little left for nonlinearity compensation. So, which is why manufacturers don't like to do it. But because of the tremendous advances with Moore's law, it is likely, because of the increase in baud rate, so 1.2 terabits, so 40 gigabits per second 2008, 1.2 terabits from commercial chips, 2.4 terabits at UCL, that gives 0.1 watt per gigabit per second. So that's, again, between 1 and 10 milliwatts per Zoom call. That's probably that's not too bad. Now, you're standing up, but I've got lots more to say. So I'm going to use my seniority to just continue a little bit more. So I'm sorry. You're free to leave, of course, but I just wanted to share with you I'm almost at the end. Can I have two more slides? Or 3 more slides, maybe? This is, so extend, I told you, so one, fighting for the signal-to-noise ratio through DSP and through ASIC development. The other is extending the fiber bandwidth. The fiber bandwidth is given by there's no hard cutoff in fiber. It's only the loss, the attenuation in silica with wavelength. And so it is possible to extend. So far, we've used the C band. C stands for conventional, which is about 4.5 terahertz of bandwidth. 4.5 terahertz. Think about all the wireless bandwidth you have. Christos, how much wireless bandwidth do you have? Sorry? I can't hear. Much lower. So this is what your data depends on. We've been able to extend it to other bandwidths. So potentially we have 60 terahertz of bandwidth. And it's at 60 terahertz of bandwidth available from the existing 4 terahertz that was enabled by the revolutionary erbium-doped fiber amplifier. And that's now over 37 years old since it was first published. And what's happened, these are just the results of throughput against distance. And just in the last 12 months, we've gone from, we in UCL have done about 20 terahertz, but we're a little bit behind. We've got some while to catch up to you by using different amplifier bands. So for all these new bands, the C band, the erbium no longer works, so you need new fibers with new dopants to give you gain in different regions. They've gone from from up to about almost 40 terahertz of usable bandwidth out of 60. So enormous developments in the world. So the other aspect is networks. How to translate this increased bandwidth that we can access in fiber into gains in network throughput. So there is Robin Matson and Rasul sitting here. There is a poster, a very interesting poster. Please go and see it in where is it? Sorry? No, it's not in Cloisters. It's in the Jeremy Bentham room. So how to translate, how to make the network intelligent, and how to find, we actually don't know what the global maximum is for a network. You give me a network, a graph, it's quite difficult to calculate its global maximum. and to adapt routing to how do you reach that global maximum. So you have a network, what the BT network, what is the maximum throughput it can support, and how do you reach it? How do you modulate and route? So for example, here's a network. You could add a good edge or a bad edge and create, if you could just increase a network by one link, you could add nothing or add 15% to its throughput. So that's actually very interesting research. So Robin is finishing his PhD and did tremendous work in this area, and Rasul recently joined them, and that's what they're working on. What about satellites? I mean, we hear a lot about satellites. There's 42,000 Starlink satellites planned. There are already about 4,500 in space. They're at low Earth orbits. And you can see them. If you use this application, you can see them. You can see where the satellites are at any given point in time, in real time. There are 20,000 OneWeb, additionally OneWeb Cooper in China Red Wall satellites. And you can see them, and you can see all the measurement equipment and the digital mess that exists in space. But all of these give a total capacity of about 100 terabits per second. That's less than one fiber. All these massive number of satellites. But what they do give is they give access, and it's probably much harder to shoot a satellite out of the sky than it is to cut a cable under the sea. So they give security. So one, I think, interesting research direction is how to integrate these networks into telecom networks in general. And the other is routing in the cloud. The industry has been very conservative. So some of the, I had in my paper, Millennium issue of Royal Society of Philosophical Transactions, Free Space Router, published in 2000, and another version of Free Space Router. But now they're just beginning to permeate into to be used in data centers. So Google Apollo announced what is equivalent to this in 2022, and there are other systems which are very, very similar, a dispersive element and a switching element. So what will data centers of the future look like? They'll have CPUs with disaggregated memory, perhaps, as argued by my colleague George Zervas. They'll have GPUs, another version of type of CPU, QPUs, quantum processors, quantum processing units, OPU, optical processing units to do matrices, and what will serve to assign tasks to them, optical networks. And how to interconnect them will also be defined by optical networks. So that network intelligence of matching demand to bandwidth and delay, because even when we're wireless, we're still connected to fiber, will maybe one day hope to maintain the growth in the relentless growth of AI. It's a question whether we need that AI and to do all those chat GPTs in inquiries to deliver capacity when and where it's needed for many applications. And just one more word about experimental verification. So we show this. This is what we use to have a world-leading laboratory in UCL 5 minutes away from the British Museum in a size of a sitting room. Okay, so just think about that. 5 minutes away from British Museum in the size of a sitting room, there's a world-leading experimental laboratory. That's what I show. It's a recirculating fiber loop because Sarah wouldn't allow me to put 6,000 kilometers of fiber all connected together. And neither would the provost, I suspect. So, or generations of them who've been and gone. And we also connected to the National Dark Fiber infrastructure facility, but that's what it really looks like. And with our multi-wavelength setup, this is what it really looks like. This is millions of pounds of equipment and 8 generations of students. And this is essentially what, the springboard to ensure the networks, the intelligent networks of the future. And so I just conclude, I'm so sorry to overrun, just by saying that the seeing through the cloud is to say that optimizing over tens of formats and hundreds of independent channels over thousands of kilometers is impossible by brute force. And the reduction of complexity is key. So the question is, does nature really compute better? Which was one of the ARIA questions. And I think the next step is the marriage of physics, digital signal processing, graph theory, and AI, and biology. So here we have a neuron. That neuron, I don't know if you've ever seen a video in the highest definition TV, which is easily gigabits per second. You see a tiger in the jungle, and that tiger is able to, so you can see the paw, he's moving the paw very slowly, and there is fur on his paw moving in the wind. Now, have you ever thought, how come you're able to detect that? Because you're detecting it through the optic nerve, which is has 10 megabits per second capacity. How are you able to process that? How much information are you actually throwing away to be able to process and route? And I think that's the way to go to kind of simplifying, making the networks more efficient, capable of supporting that data. We need to quantify the network's throughput in the nonlinear regime that we operate in, and design networks for the cloud to ensure performance and efficiency, whilst building the experimental infrastructure to verify the results for the future, for the Internet of Things, for all the applications that you use completely seamlessly, and you probably do not think about how they travel. But hopefully, now, as you go home to switch off your IoT, you will also pay a little bit of attention about what's carrying your data and how it must be, what investments must be made to continue to develop it. Thank you, and apologies for the delay.
Thank you very much.